Hello, probably you have downloaded the game maker and you have downloaded the project from entropment.com, which is the Entroper, and you probably didn't work with the game tools. They are very good for prototyping, and to show the post-quantum security in such a tool is a very nice joke. So you go to the object, there is only one object, I don't need the objects. In draw you see nothing, it is just draw a surface. So we are going here, we take a create and step event, we kill the draw, we make it bigger, and we are at home. Okay, so we have create and step event. This is the loop, and loops in loops. And here we have a setup. It will be important later on because all the tests you probably gonna need to do on the block are here. You just need to uncode them, set some parameters, and maybe inside the function you will need to change some show debug to see more. So there's a lot of those tests. Those are not useful any longer. They were made for something that is not included in the program because they were wrong. But they were about to doing something. I was testing some ideas. So the whole thing you can see, and all those random functions doesn't work, or they do garbage. So let's see what we have here. Here we have a toy model, like you can see the whole process with one key, one for every block, and decryption toy model. This is the full-blown version. This is also full-blown version, just decrypting. And because it is not a cipher, the name is different. One is entroppment and one is not entroppment. And here we have test loop for omnipotent if. She's gonna simulate that she break all the blocks because she will be stealing keys. So we send her keys for every block, the fakes 1, 2. And this is the testing loop. So first I'm gonna show how works those two. All those things are just to control the input from mouse and so on, and menu you're gonna see, and this is just drawing the menu. So this is the part we are interested in. Let's start the program. Here we have just some crappy instruction how it works, just in case you don't have the video. So the toy version works on pictures. I was testing it on the pictures, what I can do and what not. Let's take some small picture. It is visible what it is. So we have loaded the picture, and now we are choosing our kbook. They're gonna call klist for the toy version. For the full-blown version we have krig. So we are choosing klist, and we are choosing who we are sending to. So this is a choose key, and we start encrypting. It's gonna take 19 seconds. So it is taking 4x4 pixels block, and it's changing it to the floating point numbers and rotating it by the function that was described in the papers mostly. So yep, almost ready. When it is green, it's ready. So we can use this. If you turn off autosave, it's not gonna save the files. So we are copying the link, and the link is gonna send us here. I was prepared. This is the cipher. So the cipher is how many blocks and so on. There are all the information, and every block consists a scale. It is an open information in toy version, and in the full-blown also this is open. This is for to scale the vector, and there is a message. Message consists 16 imaginaries for every block, so 16 float 64 numbers. Okay, And in such a case, this is also 164 number. That's all we need. So we go to paste here. We delete this one. Okay, and we are closing our program. Start again. Let's now see if we are a cipher. We are a cipher, so we have to load the cipher. We get a cipher. Here it is. Now we are choosing who we are. So we have a K-list, and we are Eric. And as you see, it is decrypting 4x4 blocks. And because there was no data on the edge, the picture was not split by 4. So we have some border. And we have our picture. It consists some artifacts, as we see, but generally we can say this is the same picture. We can go back to our application data. It is sandboxed, and we can see our picture with the border. For human eyes, those artifacts are no problems. There are some changes I did, because for human eyes the green color is most important than the rest, and the red one is less important, so they're swapped, but generally you see the pictures. Okay, so this is a toy version. Let's delete the file. In application data it is sandboxed, so for convenience you can use files there. And now we are gonna test the full-blown loop. So let's play with that. Here we need a hardware security model simulator. We can see the keys here. There are a lot of them, but we can create a new. So we just created a new one. And this is some random keys in some random number. If you want to get to these keys, they are here. This is the file with new keys. You can use it, or we have name to set and date, but usually it is done in hardware security module, not in the program itself. Let's delete it. I have some other keys. And we're gonna encrypt some message. We don't need this one any longer. Let's take some message. We need the message to create a buffer, because we are transferring a buffer, not a message itself. So we are using a keyring, or it will ask us here for the keyring if we don't have any. If you load the wrong files, it will just crash. I didn't work on the function that are selecting if it is a good file or wrong file. This is a demonstration. So we have some string we are converting in, and now it is a buffer. Let's say it is a buffer. It is an array of zeros and ones, but we can call it a buffer. There is no redundancy now, so let's reset it and start from the beginning. Copy again, and we're gonna play with redundancy. So we are using our k-bundle. We set redundancy. We paste the string. We still can change redundancy, and we are converting into numbers. We have 105 blocks, and we're gonna get fakes around 300. Let's start. And we see the number of the blocks left are dropping. So we have to wait a bit. It is working on one core. I didn't obfuscate the code with making it multi-core, which I usually do. but it would be hard to read for people that are not familiar with such a solution. And it is not utilizing GPU, just because I have GPU that is working on the 32 bits. So here in the export we have this cipher and the new version of the key after the encryption. Here is the history key, so it would be same as our original key. Wait. Here is the key. So this is our HMS at the beginning. And here is our HMS after. This is the history, so this would be the same. Let's see number 19. Yep, same number. Okay, now after encryption, all the keys were shifting all the times. So we can see current key number 10. Where is number 10? It has nothing to do with that key. Same, 11, 11. These are completely different keys. So these are keys for the receiver, and these are keys of the sender that I rotated. So for the next message we're gonna have different bundle, and they will be coherent. Okay, let's go back to the export and let's move our file here. Start the program. We are now receiver. Entrop transcend. We are in the transcend, so we are loading our key bundle. We are loading Entroper datas. If you put wrong file, it will crash sooner or later. So we have 329 blocks, and we go for it. We know that 200 of them are fakes because we just entroped them, and so we go. So we go, and we're gonna see some the message. Now the buffer is ready, but what we have seen the candidates, it was candidates for messages. So we have back our text almost. There are some smaller, bigger errors, and there are unsorted strings that my crappy string generator couldn't found any similar, but those two for sure are the fillers for the buffer, so it is the correct size. So this is start and end filler for the buffer, but in general, as you see, there are some errors like a few bits changed of UTF-8, but in general this is the same message. Sometimes you're gonna see some cuts of the unsorted strings here, like this will be a part of this and part of that and so on. And the whole message you get here in the transcended message. Yep, it is the recovered version, it is the text. However, you're gonna send buffer and not use any function like this. Obviously you're gonna use Solomon to create buffer and to read it, and use the redundancy you like. This is just for showcase, so we have something. Okay, and now we're gonna spend a bit more time on this. We're gonna see the function for testing, because probably you are most interested in testing. So we are pasting function, we start testing, report level. Start with something low, load starting key. The key bundles will be switched between sender and receiver. You can set redundancy. The buffers will be bigger, but if you like, for test, yeah. 7 and again 1, yeah. You know what it is. So the buffer will be just bigger, but it doesn't affect the tests. It will be just very slow. And let's say some reasonable number, 5. We are not starting if, and we have a fake value of 3. But yeah, you can do whatever you like. It is against an omnipotent attacker. So let's keep it with 3 and start the if. So we can do this. Okay, and we are starting test batch and we go for the coffee. So it is started the process and now it's gonna take time. Okay, we see the test is about to get to the end. Like last round. Ready, test loop, and we are in the virtual machine, so it is quite slow. Usually you're gonna use this version. It is much faster because it is compiled. So let us see what we get from the tests. Here we have a report test loop with date, and this is a very short version, so report level 0. So what we gonna read here? It is start of every turn, and we have a k decoherence. Nothing to report, nothing happened, nothing wrong. So the k bundles after each test was correct. Otherwise, we gonna get some math numbers. And this is error average is 1.2% and minimal and maximal, so we get quite good. Bits lost in nonce, it is just because we are passing horizon. So those two. This one is included here. Total test times and so on. And we have omnipotent if. How many bits she get? So here we have 90,720 of 30,720 bits in original message, and you have to solve the puzzle which one is true. If we set fake value higher, we're gonna get much far away. So generally it is a garbage. And we have tested omnipotent attacker that break every blocks. I don't know how. This is a magic, but let's assume it is possible to break every block and find every key. Yeah, why not? So in such a case, the omnipotent attacker get a garbage. He need to solve those puzzles, errors and so on. And here we get information about one block that was skipped. Fake block creation. One was skipped because we have interference between the key that our receiver is gonna use and random key we used for encrypting a fake block. So it was the interference. How the random blocks are created. Random blocks are infused here in the encryption, and it is have a secret name of infuse random block, false random block. Here is create random bit buffer, and here it is really random, but usually you're gonna make your own function here which will resemble statistically valid block of your message. It's obvious. Or even you can put some real message that you would send just to scramble the original and encrypt it with some random key. Like random key is created here, fake 0. So hardware security module is sending derivatives of the fake key, and so you are checking it against, and if the sum is interfering with our original key, which we are checking real key here. So if the interference exists, we are skipping the block. So as we see in the test, we had one such block for 200, like that. And all the fake blocks were skipped by the legal receiver. So what you're gonna need, you can find here on DataEntroper.com, and you have all the papers if you want to make such a project. So you have text papers here. This is all algebraic things to do this, and if you need something for LLM coprocessor, it is for now just algebraic. I didn't start this, I just wrote down how to build it. Tensor for algebra optimization, of course, it is used. And here are the project hints and info, what you need to know, what to do, and how to organize such a project if you want to build yourself such a tool for post-quantum security, which is far tougher than anything we currently have theoretically, and it is using FPU as a quantum device. It was all the time for 40 years, it was all the time in the specification of EA about floating points numbers. Just we didn't use it because we were thinking it was a bug, an issue that we were solving just to not going for the nonce. And now the problem is solved. You can do this on any computer. There will be more videos about this program, so because we have more testing functions here, and I'm gonna show them later on. Yep, thank you.